So here we're going to be talking about an example of machine learning problem and employing the k nearest neighbors algorithm. And we're going to begin with the fruit data set that we're going to be working on. And the fruit data set has a number of features of fruits. So things like a mass, width, height, color score, and also the label of the fruit itself, what the fruit is. So just essentially the fruits and all these characteristics associated with each fruit. And this is the kind of framework we have worked with before, but note that we will need to determine which parts of the data are going to be the predictive features and which are going to be the predicted features, which one are going to be used as the factors to predict and which one is going to be used as the target or outcome variable. So as a regular type of data frame, each row corresponds to a single data instance. A sample, because sometimes it's called, but sometimes a sample is a number of not just one, but a part of it or group. So be careful about that. But each row is an instance. So each row is a fruit because this is a fruit data frame, fruit data set. And the fruit label is the label for each fruit. Now, the label and the name go together. So it's just one is a numeric and the other is the textual. So 1 is for apple, 2 for mandarin, I think 3 for orange, and 4 for lemon or something like that. So here we just have mandarin and apple, so I can't see, but this is the target. It's going to be the target variable, with the one we want to predict, because the whole idea is that we want to use features of the fruits to predict what the fruit is. So we could use the label or the name. So either way, I think the algorithms can work with either way because they will recognize that the target is category. And then these here, the mass, the width, the height, the color, surrounded by green. These 4 columns contain the features of each data instance that we want to use to be able to predict what the fruit is, whether it's apple or mandarin or orange or lemon. Note that fruit subtype is not, because if we already know the subtype, we already know what the fruit is. So we either want to predict the subtype or we want to predict the actual major fruit name. So these are the predictor variables in green. Just something a little bit about the color score that we're using here. So we can use a color score that goes from pinkish all the way to red. Now this is a unidimensional color score. Often we have colors in kind of 3-dimension, like RGB values. So there's a value for red, there's a value for green, and there's a value for blue. Here we just is a simplistic way to think about it. So it kind of goes from green to yellow to orange to red, and from, I guess, blue as well. Here over here around 0.25 is blue, around 0.5 is green, around 0.75 is yellow, around 1 is red. And what we have to do is we have to create we have to split the data into kind of 4 different components, and based on a training set and a test set. So the training set is part of the data, often about 75% of the data that we have. So that is 75% of the rows of the instances of the data that we're going to use to train the model. Remember, this is this is the labeled data and this is the supervised. We're talking about supervised learning. Supervised. So we do have the labeled data. And we want to create a training data set. We just split the data. We randomly select 75% of the instances. And we're going to have the X train, which is the X are the predictor features, the features we want to use to predict the outcome, and the Y train is the features that we want to predict. And here you can see, so the X train is usually going to be multiple. We're going to have multiple features, multiple columns, but the Y is just one. And you see two lines here because this is just the index. This is the index, like here 42, 48, 7, and this is the actual values. And the values, remember, 1 is for apple, 2 for mandarin, 3 for orange, 4 for lemon, something like that. So actually we just have a one-dimensional array. It's just one dimension. It's just one value for each item. But the X train, this is why we see a big here. This big X means that we have multiple. It's a whole data frame. It's not just one single array. An array is just one single dimension of values. Multiple instances, but only one dimension. So we have the X train and the Y train, and then we also have another, usually generally 25%, but you can decide on the split. You can be 80-20, 70-30, and so on, which is the test, what we call the test set. And the test set is the part of the data that we will not show the trained model. So the trained model is only going to use this data to associate all of these characteristics with particular labels, such that, okay, items 3, which is, I think it's, let's say orange, usually goes with 7 height, 7 width, 154 mass, and 0.82 color score. And if you see another 3 here, you can see, oh yeah, it is. It goes like about 7 height, 7 width, a little bit high, 160 mass, and 0.8 color score. Now if you go to 1, it's usually about 7.3, 7.6 height and width, 152, but color score 0.69. So it makes all kinds of these associations between the predictor values with a particular label. And then the test set, we won't train the model with, but we'll use to test the model. That's why it's called a test set. So the idea is that we will then use this data here, and we'll feed this, after we train the model, we'll feed the test data into the built model, and then see, well, predict this item here, predict 26, predict 35, predict this 43, predict 28, and then we'll make all sorts of predictions. And then we can use the predicted output of the model with the actual values that we have, and see how well the model performed. So the test set is to actually obtain an evaluation metric. So here we have the actual values on the test set of what they are. There's the labeled true result. And then here's what the model predicted. Well, it predicted 3, it predicted correctly, predicted 3, correct, but then this should be 4. The model predicted 1. So that's incorrect. So then the model predicted 3, it should be 3. The model predicted 1, it was 1. The model predicted 1, it is 1. The model predicted 3, it is 3. The model predicted 1, but no, it's wrong, it's 4. And so on, and you can see how much percentage it got correct and how much it didn't. So that's the idea of it. And to do that in Python, I have the Python code here, is that we will identify what the X data frame is that we want to use. Okay, so here we're just identifying 4 columns, so we're not going to fit in the whole data frame, because the whole data frame we have the predictor values, we have the target values, we have other columns we may not use. So we identify the columns or features that we want to use as predictors. So that's just a smaller data frame. So that's the X data frame. Then we identify the Y data frame. So notice that's big X. Usually we use big X because there's multiple features, and smaller and non-capitalized Y if there's just one feature, one column. And that's the feature we want to predict, is the fruit label. And so the fruits is the data frame with everything. And then we use here I'm just going to point, we're going to use the train test split function of, this is from scikit-learn, so we need to import that, and that's already imported. You see the code for how to import that, but this is the function we're going to use. Train test split, we're going to feed it in with the big X here, which is our data frame of predictor features. We're also going to feed it with the array or series, only one column of the fruit labels. And then also a random state. A random state is to tell the model kind of what number to begin in to when it randomizes the train test split. That's so if you want to do another kind of train and test split again and use the same split, you can just use the same random state number. And if you want a different, you use a different random state number. And then there's 4 things that output from that. And then we need to write this down as well. And generally we call it X train, X test, Y train, and Y test. So you got to put it in this order because that's how the output from this function is going to send it out. So notice there's like 4 objects here that is output from this function, train test split function of scikit-learn. So here we created the X from here, the Y we created from here, the random state this the parameter of the function, and then 0 is the number we chose. We can stick to that just for now, and then here are the name of the variables that are going to get the output from this function. So one thing that's important to mention here too is about examining the data. So data sets may have issues. Don't assume data is always perfectly organized with all data values appropriately structured. So issues may include, for example, misspelling. Maybe some of the fruit labels or the fruit names are misspelled, and that's going to create trouble for your algorithm because, you know, we want to make sure that we have this most data as possible and the most accurate data as possible. If some apples are spelled without a P, the algorithm may say, well, I don't know, is this an apple or not? It says a different letter. So extra characters, we kind of saw this in some previous work. You know, we have the value of for something 35, and then there's like an asterisk. Like, what's the asterisk? I don't want the asterisk, I just want the number, just the value. So you may need to move that. Or missing data, maybe some data is just missing, like for whatever reason, it's just not there. So we need to double check, well, do we want to include this in the data? Do we not include it? Sometimes there may be suspicious values. So for example, on the color score, all the values are between 0 and 1. And then here we have this 192. So what happened? This is very suspicious, and in fact, shouldn't be here at all because it's not a color score number. Or there can be wrong format or scale or data type. So sometimes we have maybe like a fruit label. Here it looks like an integer, and the program, when it loads, automatically thinks it's an integer, but this is actually it's a categorical variable. You know, in R they call this a factor. In Python, it's just it should be a string or a nominal variable. So maybe you need to change the data type for that, so you tell the program that this is categorical and it's not an integer, something like that. So you really always need to examine the data and different aspects of the data itself. Another important way to examine the data is also to see the distribution of the data for different kinds of tests, but also to understand maybe which variables are associated with each other. And here we can use this color maps from matplotlib and create a scatter matrix. So it's kind of like a scatter plot matrix. We may have used something like this before to understand both the distribution of the data and maybe get some ideas of how the data are associated with each other. So this is a very interesting function because it can do all kinds of things, but let's remember what the scatter plot is. So we have all the features of interest. We just have 9 here. So this height, width, mass, and color score. And then as with any scatter plot, we just repeat the same on the x-axis what we have on the y-axis. So on one row, we're going to have the height with the height. So this is the height variable with the height here. So this function provides a histogram of what? Of the height. So it's just one variable, height. It's not 2, it's just 1. But this is the histogram of height. And then here is, what is this? Well, this is the histogram of width. the values of width. And the histogram, of course, the frequency of the value. So many values of width is around 9, a few values are around 6, and so on. You can see the values here that you can match with. And here's the histogram of mass. You can see mass with mass. Okay, well, so what about this block here? What is this? Well, this block here is what? It's width and height. So this is the plotting of the width and the height. And actually the colors, what about the colors? Well, the colors is that we already have some information about the colors in the training data set. So actually we're feeding this into the C parameter. C is for colors here. So if you don't put this parameter, it's not going to be color. We're just going to have plots like each data point. But because we do have that information, we can actually plot the colors. So this is one kind of fruit, this is another kind of fruit, this is another kind of fruit, and we can already see that they cluster as well. But this is just plotting the height and the width. So just items, you know, this item here has low height and low width. This item here, whatever it is, has high height and high width. So we can actually start discriminating to see which combination of variables seems to help cluster, discriminate the items, the instances. And actually the height and the width seems to be a good one, right? We see like a big division here, we see a big division here. Now these two kind of are going together, so these are not discriminating. But if you see, for example, color score and height. Color score and height can actually discriminate the brown and the black a little bit better, but they are in like two different sides of the color score. So you can, with this, you can kind of get an idea of which set of features helps discriminate the items that you're talking about. So for example, this over here, what is this? This is mass and width. Width here and mass here. And notice that they do repeat. So we have mass and width elsewhere. We have mass and width here. So actually this is identical to this. This is, except turned around. It's mass and width. Notice how this does not discriminate the points that well. Like we have like 3 different groups all together here. So mass and width are not actually very good discriminating variables. But color score and width seems to be more, as we kind of do. You see that over here, whereas color score and width, no, it's over here. So notice that some of these repeat, and here we can see the histogram of the different value distributions, and also have an understanding of which variables together with which other variables can help us discriminate the different items of interest. Okay, so next we'll be talking about the KNN classifier a little bit in more depth.